This is Lecture 7, Multivariate Regression. By the end of this lecture, you should be able to understand why it is important to add control variables to a regression, understand how to interpret a multivariate regression, understand the difference between dummy variables and continuous variables, know how to interpret an R-square and adjusted R-square in multivariate regression, and know how to calculate in-graph estimates from a multivariate regression. Before I move on to new material, I would like to review some material from the previous lecture. In the previous lecture, I showed you how to use a bivariate regression to determine whether one independent variable has a statistical impact on a dependent variable. Bivariate regression produces the following equation. Dependent variable hat equals b hat times the independent variable plus the a hat. The b hat tells us the effect that the independent variable has on the dependent variable. If the independent variable has no discernible effect on the dependent variable, then b hat would be equal to 0. As the independent variable increases, the dependent variable stays the same. However, we expect the independent variable to have an effect on the dependent variable, so we don't expect the coefficient b hat to be 0. Based on our hypothesis, we expect it to be greater than 0 or less than 0. If we expect there to be a positive relationship between our independent and dependent variables, we expect that as the independent variable increases, the dependent variable increases. Hence, the coefficient b hat for this line would be greater than 0 or positive. If we expect there to be a negative relationship between our independent and dependent variables, we expect that as the independent variable increases, the dependent variable decreases. Hence, the coefficient b hat for this line should be less than 0 or negative. Now we are going to move on to discuss how we can use regression to analyze whether multiple independent variables have an effect on a dependent variable. In most cases, we don't expect only one independent variable to have an effect on our dependent variable. Instead, we expect multiple independent variables to have an effect on our dependent variable. When that is the case, we run a multivariate regression. It is called multivariate because we use multiple independent variables. Multivariate regression produces the following equation. Dependent variable hat equals b hat 1 times the first independent variable plus b hat 2 times the second independent variable plus a hat plus e hat. Note that there is what we call a partial regression coefficient, or b hat, for each independent variable. And note that the subscripts tell us which b hat belongs to which independent variable. So b hat 1 belongs to independent variable 1, and b hat 2 belongs to independent variable 2. Each b hat tells us the effect of each independent variable on the dependent variable while taking into account the other independent variables. There are several reasons why we should control for other independent variables in our regression models. First, many different independent variables can affect our dependent variable. If we leave an important independent variable out of our model, we are leaving important information out of the model. If the model does not take into account that other information, it might think the other independent variables have a greater impact on the dependent variable or a lesser impact on the dependent variable. As a result, the b hats of the other independent variables might not reflect the true b hats for those variables. For example, let's say we are interested in figuring out what factors led some voters to be more conservative than others. We think that income has a strong impact on conservativeness of voters. So let's say we ran a bivariate regression with conservativeness as the dependent variable and income as the independent variable. The b hat for income turned out to be 0.06. Now, we could say that education also has an important impact on how conservative a voter is, but we did not include it in our bivariate regression. So to take this new information into account, we add education to our model and run a multivariate regression. As you can see, the B hat for income gets bigger. Because we did not include education in our first model, we underestimated the effect that income has on conservativeness. Another reason we run multivariate regression is that it allows us to make better estimates of our dependent variable. Since we are including multiple independent variables, it allows us to take into account more factors that explain variation in our dependent variable, leading us to make better estimates of our dependent variable. And if we make better estimates of our dependent variable, that leads to a reduction in our errors. Since our estimates of our dependent variable for individual observations will be closer to the true values of the dependent variable for individual observations, our errors will be smaller, and a reduction in error leads to a higher R-squared and adjusted R-squared, meaning our models are explaining more of the variation in our dependent variable. Last, we also run multivariate regression because a significant coefficient in a bivariate regression does not mean the independent variable has an effect on the dependent variable. If the independent variable is related to the true causal independent variable, it will seem like there is a statistical relationship between the independent and dependent variable in a bivariate regression. However, the independent variable really doesn't have an effect on the dependent variable. It is the true causal variable that is driving the relationship, but we did not include that true causal variable in our bivariate regression. This phenomenon is what is known as a spurious relationship. Hence, we need to include more independent variables in our model just to make sure our results are not driven by spurious relationships. So let's say education has a true causal impact on conservativeness, but we don't know that. We just think income does. So we run a bivariate regression model with income as the only independent variable, and it turns out that income has a positive effect on conservativeness. But the only reason why income has a statistical impact is because education and income are correlated. In this case, income is acting like a proxy variable for education in the model. It may look like people with higher incomes are more conservative, but that's only because people with higher incomes tend to also be more educated, and more educated people are more conservative. If this is the case, then when we run a multivariate regression model, income may become insignificant, meaning that education influences conservativeness, not income. Now, before I show you how to run a multivariate regression analysis in SPSS, I wanted to show you how the analysis is calculated. It's important to note that I won't have you actually calculate a multivariate regression because, as you can see, it is a complex calculation. I just wanted you to have a basic idea of what the math is doing. So in multivariate regression, you calculate the coefficients B hat for each independent variable separately. Each calculation takes into account variation in all of the independent variables, just in different ways based on which variable you are focusing on. So in calculating B hat for the first independent variable x1, you take into account variations in the first independent variable x1 and the second independent variable x2. This is similar for B hat for the second independent variable. You also calculate the A hat separately. This calculation is similar to the calculation for A hat in bivariate regression. And you calculate the significance tests for each B hat and A hat separately. The significance tests in multivariate regression are the same as in bivariate regression. Now I'm going to show you how to run a multivariate regression in SPSS. Consider the following hypotheses. Hypothesis 1, as the average GNP of a country increases, the amount of resources that country devotes to defense spending increases. Hypothesis 2, Countries involved in a conflict will spend more on defense than countries not involved in a conflict. In both cases, defense spending is the dependent variable. It is measured in thousands of dollars, and we have two independent variables, GNP and conflict. GNP is measured in thousands of dollars, and conflict is measured as a 0 or 1. 0 means a country is not involved in a conflict. 1 means a country is involved in a conflict. Running a multivariate regression analysis in SPSS is the same as running a bivariate regression in SPSS, except with more than one independent variable. So you do analyze regression linear, you put the appropriate dependent variable in the dependent variable box, and you put all the appropriate independent variables in the independent variable box. Then you click OK. This is what the output should look like. The first row tells you the statistics associated with the A hat. The second row tells you the statistics associated with the first independent variable. In this case, it is GNP. The third row tells you the statistics associated with the second independent variable. In this case, it is conflict. The B column tells you the values of A hat and B hat for each independent variable. The SIG column tells you the results of the significance test for A hat and B hat. So the first thing you should do after running your multivariate regression is write out the equation. Recall that the equation is dependent variable hat equals B hat 1 times the first independent variable plus B hat 2 times the second independent variable plus A hat. So applying this to our example, military spending hat equals 335.40 times GNP minus 567,163.63 times conflict plus 576,886.56. Recall that in bivariate regression, the regression line went through the coordinate mean of the independent variable, mean of the dependent variable. The same is true for multivariate regression. The regression line we just calculated passes through the coordinate means of all the independent variables and mean of the dependent variable. After you have written your equation, you need to interpret the significance tests for the coefficients B hat. In this process, you will examine each coefficient separately. Recall that when we interpret B hat, we want to know if it is different from 0. If B hat is not different from 0, there is no relationship between our independent and dependent variable. As the independent variable changes, the dependent variable stays the same. If B hat is positively different from 0, as the independent variable increases, the dependent variable increases. And if B hat is negatively different from 0, as the independent variable increases, the dependent variable decreases. So to show you how to interpret the significance test for B hat, I will use the multivariate regression analysis from earlier in the lecture. Recall our regression equation was military spending hat equals 335.40 times GNP minus 567,163.63 times conflict plus 576,886.56. So we want to know if 335.40 is different from 0, and we want to know if negative 567,163.63 is different from 0. Recall that these rows tell us the statistics associated with the B hat for each independent variable. The B cell here tells us what B hat is. First, you should look at the sign of B hat. If it is not in the expected direction, then B hat is not significant and is indistinguishable from 0. So let's say you expect the independent variable to have a positive effect on the dependent variable, but B hat was negative. Then your B hat is automatically insignificant. You do not have support for your argument. If your B hat is in the right direction, move to the next steps. Okay, so the next step is to look at the results of the significance test for BHAT and SPSS. This last column here, sig, tells you the sig value for each BHAT. If the sig value is less than 0.002, then the coefficient is significant and different from 0 at the 0.001 level. If not, move on to the next step. If the sig value is less than 0.02, then the coefficient is significant and different from 0 at the 0.01 level. If not, move on to the next step. If the sig value is less than 0.10, then the coefficient is significant and different from 0 at the 0.05 level. In all of these cases, you have support for your argument. The only difference between these three levels of significance is if your significance test meet these criteria, then your results would be significant at the 99.9% level. If your significance tests meet these criteria, then your results would be significant at the 99% level. And if your significance tests meet these criteria, then your results would be significant at the 95% level. Now moving on, let's say your sig value was greater than 0.10. That means your coefficient is not significant and is indistinguishable from 0. You do not have support for your hypothesis. An important note before I move on, anytime you see a sig value of 0.000, that is less than 0.002, so you have significance at the 0.001 level. So applying this exercise to our regression example, we expect GNP to have a positive effect on military spending. The BHAT was positive, so we can move on to the sig value. The sig value, 0.00, is less than 0.002. So the coefficient BHAT is significant at the 0.001 level. Now moving on to conflict. We expected conflict to have a positive effect on military spending. Yet the sign of BHAT is negative. So the coefficient BHAT is insignificant. It is not distinguishable from 0. So we do not have support for our hypothesis. If the coefficient BHAT was insignificant, you cannot make any conclusions. You do not have support for your hypothesis. If the coefficient is significant, then you can interpret it. If it is significant, then you start by indicating what level the coefficient is significant at. You indicate if the variable has a positive or negative effect on the dependent variable, all else equal. All else equal is just a very concise way of saying that you have taken into account the effect of other independent variables in your model. And even after doing that, this independent variable seems to have a statistical impact on your dependent variable. Then you state the substantive impact of your independent variable on the dependent variable. The substantive impact of the independent variable on the dependent variable depends on what type of variable it is. Up until this point, I have shown you how to interpret regression coefficients for continuous variables. A continuous variable is simply a variable that can take on multiple values, such as 0, 1, 2, etc. So to interpret the substantive impact that a continuous variable has on a dependent variable in a multivariate regression, you write all else equal, when independent variable 1 changes by 1, the dependent variable changes by the value of the coefficient BHAT1. So now we can apply this to our multivariate regression example. Recall that the coefficient for GNP was positive and significant at the 0.001 level. We would say that the coefficient for GNP was positive and significant at the 0.001 level, all else equal, as GNP increases, military spending increases, and all else equal, as GNP increases by $1, military spending increases by 335.40. Now, Not all variables are continuous variables. There are many different types of variables, and we have to interpret them differently than continuous variables. In this lecture, I will show you how to interpret dummy variables. In the next lecture, I will show you how to interpret other types of variables. So a dummy variable is a variable that only takes on two values, 0 and 1. In our multivariate regression analysis, we had a dummy variable conflict. It only took on two values, 0 and 1. When you interpret a dummy variable, you first indicate what level the coefficient is significant at. You indicate whether the variable has a positive or negative effect on the dependent variable, all else equal. Then you state the substantive impact of the variable on the dependent variable. Basically, you divide the observations into the two categories of the independent variable, and you say, all else equal, the average difference in the dependent variable between observations in category 1 and category 2 is the value of the coefficient b hat. The value of the coefficient applies to observations in category 1. So let's apply this to our multivariate regression example. Note that the coefficient for conflict was not significant, so we should not make any conclusions. But if it were significant, we could say countries involved in conflict, the one category, spend 567,163.63 less on military spending than countries not involved in conflict, the 0 category. Now moving on to interpreting the constant a hat. Recall that a hat is also the y-intercept. In this equation, it is 576,886.56. Interpreting a hat in a multivariate regression is similar to interpreting it in a bivariate regression. We do not have an expectation about whether a hat is positively or negatively different from 0, so we just assess whether it is positively or negatively different from 0. So to determine whether a hat is different from 0, we look at the sig cell here for a hat. Then we compare the sig value to these rules. Note that these rules are different from the rules for determining if b hat is significant. If the sig value is less than 0.001, the constant is significant and different from 0 at the 0.001 level. If not, move on to the next step. If the sig value is less than 0.01, then the constant is significant and different from 0 at the 0.01 level. If not, move on to the next step. If the sig value is less than 0.05, then the constant is significant and different from 0 at the 0.05 level. If not, then the constant is not significant and is indistinguishable from 0. Also, note that any time that you see a sig value of 0.000, then it is less than 0.001 and the significance is at the 0.001 level. Applying this to our example, the sig value for the constant was not less than 0.05, so the constant is insignificant. It is not different from 0. However, if it were significant, we would say that it is significantly different from 0. We would also note at what level it is significant and whether it was positive or negative. Another way to interpret the constant a hat is to say that a hat represents the value of the dependent variable when all the independent variables take a value of 0. You should only do this if a value of 0 for all the independent variables makes sense. So recall our multivariate regression example. Military spending hat equals 335.40 times GMP minus 567,163.63 times conflict plus 576,886.56. We could say that a country with a GMP of 0 that is not involved in conflict spends 576,886.56 on its military. However, this is unrealistic because no countries have a GMP of 0, so in this particular case, we should not interpret our a hat this way. Now on to interpreting the R-square in multivariate regression. It is almost the same calculation as in bivariate regression. The only difference is that now we have multiple independent variables in our models. Recall that the R-square of 1 means that our model perfectly estimates our dependent variable, and an R-squared of 0 means that our models cannot estimate our dependent variable. Now I'm going to show you how to interpret the R-square in multivariate regression. Suppose our R-square was 0.12. We would move the decimal place over to the right twice and treat the value as a percentage. So in this case, we move the decimal place over twice and get 12%. Then we would say that variation in all the independent variables explains R-squared percentage variation in the dependent variable. Or in this case, we would say variation in GMP and variation in conflict explains 12% of the variation in military spending. The adjusted R-square in multivariate regression is also similar to the adjusted R-square in bivariate regression. Recall that the adjusted R-square takes into account the sample size and number of independent variables into account. Now I'm going to show you how to interpret the adjusted R-square in multivariate regression. Suppose our adjusted R-square was 0.11. We would move the decimal place over to the right twice and treat the value as a percentage. So in this case, we move the decimal place over twice and get 11%. Then we would say that after taking into account sample size and the number of observations, variation in all the independent variables explains our adjusted R-square percent variation in the dependent variable. Or in this case, we would say that after taking into account sample size and the number of observations, variation in GMP and variation in conflict explains 11% of the variation in military spending. Now I'm going to show you how to calculate estimates in multivariate regression. When you calculate estimates, you make predictions of the dependent variable while varying only one independent variable that was significant and holding the other independent variables constant at a specific value. So let's say I wanted to make estimates while varying the first independent variable. Then I would make sure to hold the second independent variable constant at a specific value. You can choose which value to use to hold the other variables constant at. The value should be meaningful. For example, you can use the mean of the independent variable or use the extreme values of the independent variable. You get to choose which value you put here. So first I'm going to show you how to calculate estimates while varying a continuous variable. Remember that continuous variables can take on multiple values such as 0, 1, 2, etc. Recall our multivariate regression equation example. Military spending had equals 335.40 times GNP minus 576,163.63 times conflict plus 576,886.56. I want to vary GNP, so I keep GNP in this equation. Then I set conflict equal to 1, so I put a 1 here. Using this equation, I go through each of my observations and insert the value of GNP into each equation. So for observation 1, GNP was 478.1. So I put 478.1 here, and I get 335.40 times 478.1 minus 576,163.63 times 1 plus 576,886.56. And the answer is 170,077.7. For observation 2, GNP was 376.8. So I get 335.40 times 376.8 minus 567,163.63 times 1 plus 576,886.56. And the answer is 1283170. And I would continue doing this for each observation. To do this in SPSS, the first thing you should do is write your equation down on a piece of paper. So I would write down 335.40 times GNP minus 567,163.63 times 1 plus 576,886.56. Then you would go into SPSS and do transform compute. You would write estimate in the target variable box. Then in the numeric expression box, you would type in the equation. So in this case, I would type in 335.40 times GNP minus 567,163.63 times 1 plus 576,886.56. Note that I did not include any spaces in this equation, and I used the exact variable names that SPSS uses. If you do not follow these rules, SPSS will not calculate your estimates. Then you click OK. Now SPSS has created a new variable called estimates in your data set. Now you can plot your estimates against your independent variable. You do graphs, legacy dialog, scatter dot. You choose simple scatter. You place the estimate variable in the y-axis box. You place the independent variable you varied in the x-axis box. In this case, it would be GNP. Then click OK. Then you interpret the graph. Here I can say that if a country is experiencing a conflict, as GNP increases, military spending increases. Note that I made sure to note that I set conflict equal to 0 when I said when a country is experiencing a conflict. When you interpret your graph, you must note what values the other independent variables are being held at. Calculating estimates for dummy variables is a little different. Recall that a dummy variable only takes on two values, 0 and 1. So we will only have two estimates. To demonstrate how to do this, I will use our multivariate regression example. I will focus on making estimates while varying conflict and holding GNP constant at its mean 8,375.8. Note that conflict did not have a significant impact on military spending, so we should not make estimates based on it. But we will do so in this lecture just for demonstration purposes. So the first step is writing our two equations, varying conflict and holding GNP at its mean. The first equation would be military spending hat equals 335.40 times 8375.8 minus 567,163.63 times 0 plus 576,886.56, which equals 3386129.88. Then our second equation would be military spending ad equals 335.40 times 8375.8 minus 567,163.63 times 1 plus 576,886.56, which equals 2,818,966.25. Note that the only difference between these two equations is the 0 here and the 1 here. 0 is for countries not experiencing conflict, and 1 is for countries experiencing conflict. Then we would say when a country has an average GNP, it spends 3386129.88 on its military when it is not involved in a conflict. And when a country has an average GNP, it spends 2,818,966.25 on its military when it is involved in a conflict. Note that I made sure to note that I set GNP equal to its mean here and here. When you interpret your two estimates, you must note what values the other independent variables are being held at.